So, recording in progress, good. Thank you everyone for being here. It's my pleasure to introduce Paul Raschky from Monash University. Paul is an associate professor and is the director of the Soda Labs. His work spans political economy, environmental economics, and development economics, and his some fascinating work that that's already out there and some that he's working on. So I'll encourage you to look up his website and take a look at his papers. Paul, as I said, 1 hour, 15 minutes. You can defer the questions to the end or take them as you go along. So welcome, Paul. And with that, the mic is yours.
Yep. Thank you, Tushar, and all the others for inviting me. Regarding the questions, I'm happy to take questions in between, but I don't think that I see the questions that appear in the chat. So either one of you, if you want to interrupt me to say there's a question in the chat, I'm happy to take them along. Okay, so yes, this is a joint project with my colleagues Klaus Ackermann, Nandini, Alexei, and Miti. We are spread across 3 departments, 2 faculties, but our uniting sort of umbrella is Soda Labs, which we founded about 2 years ago. And I think this is one of the projects that kind of showcases the idea behind Soda Labs, that certain type of research in economic requires tools to analyze data and computational capacity to analyze data that economists normally don't have. And so basically you try to find other people who do that to conduct that research. And that's basically a nice way to say that most of the very interesting and more exciting things that you will see in this presentation is done by all the young people on the team. And I'm just the old person there. And as the title suggests, it's about measuring economic development using daytime satellite imagery. And the project is very much work in progress. Okay, so just to motivate the paper, I guess to the audience here, I'm saying nothing new, that if we want to do empirical research about economic development, we require some sort of indicators about such development, both at the national and subnational level. And that's important not only for us as researchers, but eventually for policymakers as well, because we want to decide where to allocate our scarce resources. The issue is when it comes to developing countries where questions of economic development are particularly essential, the data availability and quality is relatively poor. It has been improving over the last decades, but it's still data, especially at the subnational level, is relatively scarce. So at the national level, when we think about aggregate accounts data, that is 2 books by Gerben, who argues that especially developing countries lack good statistical capacity to collect this data in a reliable and consistent way. Then there are these issues of politically motivated misreporting, and there are various incentives to do so. I mean, there's plenty of discussion about how reliable is GDP data, especially provincial GDP data in China, or the incentive when you think about aid recipient countries to report truly their level of economic progress. And then there are these nice anecdotes in the book that show when you look at this aggregate accounts data, there are these really revisions, and often these changes in the revision are really large. I mean, you talk about double-digit changes in revised GDP data from one year to another. When you go down at the subnational level, which this paper is about, there's this one Journal of Economic Growth paper by Jenny Olish, Life, and others, and the data is publicly available about growth in regions, and they compiled from a very large set of statistical agencies around the world subnational GDP data. And when you look at that, you see that it's very limited, and especially when you look to Africa, they only have a handful of countries there, and it's very coarse. So for example, for Nigeria, they split the country into 4 big regions, and you have some GDP data there. What a lot of us have been using is in general broadly speaking, household surveys of ground data. The most popular one is, of course, the DHS data, where we have survey data at the household level. Now, one issue is when you think about aggregate economic activity or development, this mainly represents the C in our equations. It mainly represents, they create indicators of household level wealth, which is, of course, a good proxy of economic development at a certain level, but leaves out, a lot of other parts. And of course, these surveys are relatively infrequent. They're not conducted in every country, and even within country, they're only conducted in some areas. So you have the issue that they are not, when you want to go down to the subnational level, although they might be representative at the national level, they are not representative at the subnational level. Okay, so a workaround that researchers, but also international institutions and countries have done in recent years was to look at so-called passively collected data. And one thing that has been relatively booming is using remote sense data or satellite imagery of nighttime luminosity. And there's since the past 10 years, there's quite some growing literature that shows that nighttime luminosity is correlated with national and subnational GDP. And there's, there are now a lot of papers using this nighttime lights data as a proxy for local economic activity, in particular in Africa. And the neat thing about it is you can actually use this data with relatively limited GS skills. And so that's once this initial barrier of entry was reduced, people have been widely adopting that data. Now, when you look into this data more closely, there are a number of issues, of course. The first one, the first caveat is the so-called top coding problem. So the issue is at least with the first generation of nighttime satellite data, when you look into very developed countries, think of London, the data is top coded at 63. So the number is 63. And this doesn't change. So even if economic development in central London further increases and grows, it will stay at 63. And Richard Blum and Melanie Krause have a nice paper on that called Top Lights. The second caveat, which is more relevant for poorer countries, is what I would call the bottom coding problem. And the idea is that when you look at poorer countries, and within those poorer countries at low output, low density regions, satellite images don't necessarily provide a good measure for economic development, simply because the light that's emitted by consumption, investment, and government expenditure in these countries and regions is not strong enough to be picked up by satellites. So it's just a mechanical problem. And somewhat related to that, there are a number of very recent papers that highlight a lot of other problems, especially when it comes to using this data for very poor countries and very poor regions. And what this paper is about is somewhat, trying to address this bottom coding problem. So just to give you an idea what I mean by that, I have here an example of a district or a town, city in Rwanda called Kansense with approximately 20,000 inhabitants. So on the left-hand side, you see the zoomed out daytime picture. On the right-hand side, that's the zoomed in picture. And we can see, there's proper houses, maybe some industry there. And when we overlay the left one with the picture with the nighttime light data, it looks something like that. I zoomed in, so the scale between the left and the right is not the same, but just to give you an idea. Okay, that's what we would see of Kansense at night in the nighttime luminosity pictures. Here's another town called Mugina in Rwanda, the same size, 20,000. You look at it, you see some residential buildings, some storage areas, things like that on the left-hand side, and that's the nighttime light picture on the right-hand side. And so this is, something basically mechanical. These are the things we have in the nighttime light data that we use. I've used extensively And that's this issue with bottom coding. And as I mean, 20,000 inhabitants is not a small town. Yes, so that's basically the issue. Now, not just since people have, highlighted this problem, but even before, there has been a relatively large literature in remote sensing that looks at feature extraction from daytime images. So our colleagues in geography and related fields, and what they have done is actually they spend a lot of time, and that's basically the bread and butter, for example, to what I would call a single object focus. So basically they improve algorithms to detect roads or houses or trees in a very small geographic area. So they get a very limited set of satellite pictures and try to count trees, for example. And that's this whole remote sensing literature there. And there's been an increasing use of daytime satellite imagery in economics. So Dave Donaldson and Adam Storregard have this nice Journal of Economic Perspectives article that provides a good overview. And very recently, it has been widely used for people in urban economics, for example, to identify urban boundaries or detect urban markets. So the Bharadwanath paper with Gordon Hanson is a recent example where they look at, try to identify urban markets in India, for example, using daytime images. And most recently, there are some advances, and that's the literature where we fit in, where people have used daytime satellite imagery to do poverty mapping. So there's the science paper by Shan et al., which we relate most to, a very recent one by Jay and Marshall Berg for Africa, and then for some other countries. Now, when we focus on the Shan et al. Paper, because that has been a pretty big sort of step forward in this area, what they basically do is they apply modern statistical learning tools, machine learning, to extract various features from daytime satellite imagery. And the way they do it is the following. So they take Google Maps or the Google Earth images. And why do they take it? Because it's freely available. And they split it up in rectangular grids of 400 times 400 pixels. The pixel is, when you take a photo with your camera, the resolution is, in pixels. And this grid cell is about 1 square kilometer. And then they train a detection algorithm on images from ImageNet, which is an image database on the internet, which has like 14 million images. And you have everything in there. You have, of course, it's the internet, so there are a lot of cat pictures in there, but there are a lot of other images in there as well. And they, in order to train a computer to detect something to detect features from an image, you need to have some, something to refer to, and they use this image database. And they combine basically in the next step the daytime images with nighttime images to identify area of man-made structures. And the idea there is, when you look at a picture from outer space for Africa, there could be gray rectangular areas, and they might look like a house, but if you look closer, they could be a subset of stones and rock formations, okay? And if you as a human look at that, you can identify that, but for the computer, even if you train it on a subset of a lot of other, random images from the internet, the computer might still think it's a house because it's a rectangular area and it's gray. So they said to avoid all that, we overlay it with nighttime imagery, nighttime lights, because we know whenever there's nighttime light, it must be man-made, okay? And then they extract 40,000 features that includes information on roads, water and urban ways, and buildings and so on. And what they do then is they use those features and predict basically asset scores from the DHS data. So the household survey data, the wealth index is there. And then they provide an out of sample prediction for 5 African countries. Okay, so that's what they do, and that's our baseline. Now, the caveats, of course, is that the first one is that they train their detection algorithm on ImageNet, but not on actual ground truth. They say we have an image database that's labeled house, and we use that, but not that many pictures actually in this publicly available database has the bird's eye view of objects, because these are not images that you easily get. So that's one thing. And the other thing is that their approach requires nighttime light data, as I mentioned, because they want to avoid that the satellite or the detection algorithm considers rock formations for a big urban agglomeration, which of course is a problem because it doesn't solve our bottom calling problem. So this one town in Rwanda that I showed you would not appear in their setting because it's coded 0 with the nighttime light thing. So they would consider there's no man-made infrastructure there. And they only apply this approach to DHS clusters for 5 African countries. Okay, so our goals in this paper is first of all to improve on their algorithm by training it on ground truth data. And then we use satellite images using the same pixels to attract features based on the improved algorithm. Then the first step is we use these features, and instead of sort of directly regressing it on GDP, we say that what we extract is nothing else than fixed capital. So basically we use that then actually to predict fixed capital and apply a growth accounting approach to predict subnational GDP for Europe at the NUTS 2 level. Why are we doing that? We make the assumption that at least the NUTS 2 data from Eurostat or Cambridge Econometrics is one of the most reliable GDP data that are figures that we have out there. And we want to show whether our approach, is useful. However, one can say, well, why do we do all this fancy satellite stuff for Europe? And it's just to make, it's more of a proof of concept to say, when we use, there's a lot of belief we put in there to say we take satellite data, try to predict fixed assets and see whether this can help us to predict GDP. And what I would like to show you that using this data, we are doing actually pretty good in predicting local GDP. But then the neat thing, the big goal, and now that comes in italic because that's more the work in italics because that's the work in progress thing. We want to use this approach to make an out of sample prediction for Africa at the grid cell level, and I'll come back to that later. And then in the next step, we want to say, once we have this predicted measure for local economic activity, we don't dare to say that we would predict GDP at this stage. We replicate the Henderson et al. QJE paper that uses nighttime light, and we replace it with our local economic activity to see how their results differ when we use our new measure. But as I said, the last two ones are really the very much work in progress ones.
So Paul, can I ask a quick one?
Yeah, please.
So with the Jean et al. Paper, if they're training their algorithm with this database that's available online, most of these images come from developed countries, if at all, right? And so the houses in Africa from top will look very different from, say, Australian houses, right? So your out of sample prediction, do they provide any evidence that it does well in all settings or no?
Well,
and does your algorithm improve on that as well?
Okay, so we don't actually so it's on our to-do list that we do a direct comparison with the feature extraction that they do for Africa. So the short answer, as of now, we don't have this direct comparison to Jean et al. To see who does better. We do our own thing, and as I can show you to say how well does our approach do to predict features, and I hope I have some evidence to say it does pretty well. But you're making a good point in terms of looking at the ground truth data, that the ground truth in Europe is different to the ground truth in Africa. For them, you're absolutely right. The ImageNet thing is very heavily biased towards Western countries. To some extent, our approach has the same problem because when I will show you about the ground truth data, that's mainly for Europe. And of course, buildings in Europe and Africa somewhat look different. But then we also have additional ground truth data for Africa as well, on which we train our algorithm on. That again comes with some caveats, but I think it will come a bit clearer when I get to this point.
Thank you.
Chris.
Yeah, thanks, Paul. Just a quick question. I mean, there's going to be a lot of activity in Africa, which is kind of smallholder agriculture, mining, alluvial mining, all kinds of things that might not necessarily have fixed capital and or night lights. Is your algorithm also going to be trained on those kind of activities? Because at a small scale, they probably add up to quite a lot.
Yes, and the answer is no. We for sure miss a lot of things that are economic activity, including what you said. So any mining activity, especially underground, we actually haven't looked into detecting mining activity, for example. That would be something to add on. There are, the further you think, the more you think about, we are not, with this approach, we are not able to measure any activity that happens in those buildings or on roads. True. All these things we are unable to measure. I mean,
so I'm just thinking things like cassava. I mean, you'll have cassava processing plants, and there'll be some bit of capital there. But other things could probably be captured by looking at differences over time if you've got daytime data. But anyway, I'll leave it there.
Yes. Yeah. And also a good point. So far, we only do cross-section. There are, simply for data limitation reasons, but that would be then the next step to build a panel. But you're absolutely right. Yeah, I mean, that's, again, using daytime images is no panacea for all our data problems. We are still very far from anything close to very detailed in terms of what we are picking up. But let's say we think it's a good proxy, and that our goal is, I think, our benchmark where we want to improve is on this situation, to say that so far we think there's zero economic activity. Can we move?
Understood. Yeah. No, understood. Mm-hmm. I'm sure in the future you've probably got a whole work plan ahead. But anyway, sorry. Thank you.
Yeah. No, thank you. But this, I mean, that was a good comment. So the roadmap for the European data, and the thing is, for those of you who don't work with geographic data or subnational units, I'm jumping around at different subnational areas. So, please tell me if I lose you. So for Europe, we basically use two geographic units. The first one is so-called grid cells, which is a rectangular area of roughly 1 square kilometer containing 400 times 400 pixels. The pixels is our photo. That's where we get the satellite imagery from. The actual economic data from Eurostat is at NUTS2 regions. That's roughly the second subnational level in Europe. It's sort of standardized regions in Europe where people have put in effort to provide for, a set of these 25 European countries, a set of subnational GDP data. And in addition, we have data about fixed capital in there and some other things there. So what we do in the first step is we identify fixed capital features from open source data at the NUTS2 level, and identify those features in the open source data that help us predict fixed capital in the best way. And then we use those, our daytime satellite imagery, and we extract features from the daytime satellite imagery to predict fixed capital at the NUTS2 level. And then we use the predicted capital in a basic development accounting approach to construct subnational GDP, basically combining it with the population data and TFB information. So that's the first step. And then we basically, we just regress the official GDP on our predicted GDP and see how well we do. Okay, that's the sort of proof of concept stage. Okay, like, how do we do that? So that's one of these images that you can get from Google Earth. This is a picture of Holland. And now the big goal is, of course, to say we want to identify the things there in this image. And for the human eye, we can say, well, this is a highway, this is a residential road, and here are a lot of buildings. Most of them are probably residential. Now, the idea would be the gold standard, or put it that way. For Europe alone, we have 28 million of these images. And so we can't just have an army of RA trying to count houses and roads here. So we have to train a computer on that. But for that, we need ground truth data. Now, the idea there would be that ideally what we want to have is people who would go around and collect this ground truth data in the following form. So here is a coffee place in St. Gallen where I've visited my co-author. It's next to the university, and it's the Schweiter Unibeck, as the Swiss would call it, and it's a bakery. And so we would basically want someone to go around with a GPS, go there, put in the geolocation to say this building is located here, and add some information. So add longitude and latitude, maybe give it a name and classify it as a coffee shop, okay? And then if we would plot that, we would get a point information based on the longitude and latitude. And when we overlay it with the satellite data, that's the building from top. So you see here these features, and that's basically the, it had this corner thing here, and then it would basically say that that's the Schweiter Unibeck. Now, luckily for us, this is actually done by OpenStreetMap, which is some of you might or might not have used. And it's an open source mapping project that basically combines publicly available maps. So there's a lot of data from our local councils and institutions at a higher federal level across the world that provides exactly this information already. So it provides for each street, for example, not just point, but also line data on where the street runs and what type of street it is. And then it has zoning, so on and so forth. But the neat thing about OpenStreetMap is that there's a community of roughly 5 million people around the world, and around 1.3 million of them are actually very active, and it's their hobby to go around, collect, store, and georeference the ground truth data. So I'm not the one judging hobbies, but that's amazing. So this is very nice that people do that as a hobby. And so that's it. It's not just because it's open source, but companies like Facebook, Craigslist, and so on have actually switched from using Google Maps to OSM. So it's a very reliable tool. And very often, so there was this earthquake in Haiti where this OSM data is, for example, being used by the UN and the World Bank because they didn't have reliable, updated maps on houses and streets. So this data has actually 77 categories. So the classes, buildings into residential, commercial, public buildings, various road classifications, rail, waterways, airports, so on and so forth. So when we overlap now our image from Holland with the Google, the OSM data, it looks like this, okay? And that's something we can work with because that's data, that's actual data we can analyze. So in this case here, I take a smaller picture. The red square is the grid area. The brown thing are various transport infrastructures. And here we would say, 40 buildings and 4,000 meters of road length and some rails, okay? And then here it's even more detailed. I mean, that's the thing. People measured that. And I mean, in St. Gallen, because it's Switzerland, people even geolocated official post boxes and things like that. But there's some variation in, coverage quality. But for Europe, that's the first thing where we train our algorithm. The coverage is actually pretty good. Okay. So out of the 77 categories, because at the end of the day, even though we now have ideally some ground truth data, as I said, for Europe, we talk about 28 million images that we need to run for a big computer to extract these features. that would have taken very long if we would say all these categories are relevant to predict fixed capital. But for example, there are some categories in there where we can see that they are not, they don't do very well. So what we first did was simply we used our at the NUTS2 level, we just calculated the total sum of the features in each NUTS2 and ran a random forest classifier to identify the 18 relevant categories that help us to predict fixed capital. Why do we use random forest classifier? First of all, because my young colleagues prefer that, and it performs a bit better than OLS. Alternatively, you could just regress fixed capital on these 77 categories and see what works. At the end of the day, we find residential, commercial, public buildings, railways, so on and so forth, do very well in predicting those categories. Okay. Now, the big thing is that accessing the raw data, so it's publicly available by Google Maps, but what we had to do is to define this script, 1 × 1 kilometer, overlaid with the boundaries for European countries to define the spatial extent, and then basically do a lot of queries with Google's API. One problem is that Google is, in a sense, very open with their data, but they don't want someone to extract the complete database. So we created a few hundred fake APIs to just get the data down. And we downloaded basically these 28 million images. And then we started off by, so the Shan and Al algorithm is publicly available. And we started, that was our basis, and we improved it. And the way we improved it, I come back to that in a second, and we used, Monash has some nice computing infrastructure, so Klaus did all that. And we got a grant from NVIDIA. So for those people of you who play computer games, NVIDIA like these graphic cards, and their form of research grants is that they provided us with 14 high-end graphic cards to work on that. Now, the basic idea behind the feature extraction is that when you look at a satellite image, it's what computer scientists would call highly unstructured and high-dimensional data. And all these modern tools, what they do is at the end to translate unstructured in more structured data. Now, in a nutshell, again, I'm no expert in these new methods at all, but just to give you a basic idea, we use something called CNN, or convolutional neural network, to basically split this image into various layers, and over these layers we basically run filters, and to detect specific patterns, graphical patterns. And so the very most basic filters detect just edges and corners and circles. And so when you do an entry course in these methods in Python, what you start off with, for example, is a headshot of a person behind a blurry background, similar to me, where on the picture you can nicely see the edges around there. And you start off by applying these tools to build a filter that basically identifies the edges around your head. Okay. And that's just a very naive form. So that's how far I got. Now, the way you can think of it is each picture is basically pixels. So in our case, we have 400 × 400 pixels. And within these pixels, it's way more small. And you have just, at the end of the day, shades of gray. And in the smallest form, how this filter works is you build a filter that's a 3 × 3 matrix that slides over this image, and each filter is a particular task. So let's say just identify edges. And the way I have illustrated it here, so we have here 4 different satellite images. And below here, the result of running various filters over them. And in this one, we had a filter that, is good in identifying certain brighter shades. So you see the dark areas here is wood, and the filter basically just identified the lighter shades here. And then here we had another filter that gets down in identifying edges of houses and buildings way better, and so on and so forth. And so the idea basically is you can just run filters, CNN over satellite images to identify edges and lines and things like that. That's the first approximation, but having our ground truth data from above here, that helps us to say if you have a feature that looks something like that, it's more likely to be a residential building or a building. And if you have a line that runs something like that, it's a road. So we did that. We did that on a random subsample for images for 25 European countries. Then we used the random subsample for images in the more southern, quote unquote, poorer regions of Europe, with the idea that building structure might look different and things like that, and use then the rest of the sample for the out of sample prediction. Now, in terms of coming back to Tusha's question, how well do we do? So here we have an image of, actually, I don't know where in Europe. On the southern end, you can see the houses. And in that area, basically, based on the ground truth data, we have 9 buildings, and our algorithm predicts 8.5 buildings. Okay, so even here, so why I'm showing this, first of all, just in terms of you have relatively dark colors, so identify, it's not very clear just from the differences in colors where the houses are, and you have a lot of other rectangular areas here already that a naive algorithm would say, hey, that looks like a house. But the actual houses are just down here, and the algorithm does relatively well. Of course, that's cherry picking. So if we basically plot our predictions on the total building count, we actually do fairly well there.
So Paul, what's the time lag between like the OSM data when you source it from and this satellite imagery that you use?
Good question. I mean, it can be a few years. For the Google satellite data, we used in most cases the most recent thing that's available there. And OSM data, I mean, we'd used the most recent download at that time, but we don't know when it was there. So yes, so for sure, I mean, it's a good point. The time lag is an issue. And of course, there are differences between, even in Europe, that some cities don't have that many OpenStreetMap followers. So some of the ground data collection is not as detailed. Yes. Yeah.
But also there's this deeper point about some regions in developing countries that are moving at developing at a faster rate, right? The rate of change in terms of the buildings will be much higher, right?
Yes. So good point. So one thing, we initially started just with the Netherlands because it's a small country, and according to OSM, there the coverage is the best. There's not that much difference with the building prediction just with the Netherlands compared to other European countries. But you're making a good point. It's all these are issues with when it comes to developing countries where simply the prediction accuracy is not as great.
Yeah, so what I'm more interested in is basically, since we have a prior that some regions will be changing more over time than others, is there a way to adjust this algorithm for that? We know where the bias is in one direction, right?
Yeah, I mean, so I'll put it the other way. So it's actually less of a concern because we use, I mean, as long as we, in the existing ground truth data, we have a large enough variation of how buildings could look like. And we have easily that.
Yeah.
Because we use that ground truth data to train our algorithm to find buildings of all, and roads of all shapes. Yeah. So as long as we have a large enough set of ground truth data, which we easily have, then it's fine. Of course, on the margin, we could always improve that. Where it is an issue, however, which is a good point, is then that we have to think really hard of what we see here, because the total building count is based on the OSM data. Yeah. And these are our prediction on what is truly on the ground. So it's hard to say whether the differences, any distance here from the 45-degree line, whether it's because our prediction thing is not perfect, or because the total building count is not the correct one.
Just to comment, Paul, on
yes.
the previous chat, you just flashed the previous one, not this one. Yeah, this one. So just observation here, it seems that for lower capital, you tend to over-predict. For higher capital, you kind of under-predict.
Okay, yes, I haven't been, yes, let me, but Trusha, have I answered your point? Yeah, okay. So yes, in the next step, what we did here is, so we took this data, the 17 categories that we identified before, whether they're relevant, we aggregate them up at the NUTS2 level.
Yeah.
And then basically combine these aggregate accounts with the official fixed capital data and predict basically the fixed capital at the NUTS2 level. And Jan Rui, you are absolutely right. We are doing very well in this area here, but when it comes to NUTS2 regions with high amounts of fixed capital, which are the high intense areas, we don't actually perform as well. And there can be many reasons for that. One reason, for example, is that we don't know what's in those buildings. So, areas in Europe with high fixed capital could be, still manufacturing heavy areas where, a storage hall, you don't know whether that's a storage hall that just stores some scrap metal, or it's actually a steel mill where the true value is not the house, but the machinery that's inside. Yeah. But still, I mean, we are relatively happy with an R-square of 0.73.
A quick question, Paul.
Yes.
So when you're identifying buildings, I'm assuming this is the extensive margin, right? You either identify them or you don't. But as far as the question of, say, for example, vertical development is concerned, how high the building is, or how many stories there are, that I think is again a question that might actually explain why in high capital intensive areas, you probably are under predicting, right?
Yes, good point. Yes, that's again one of the reasons. That's again, we can't. I mean, that's the disadvantage of this data.
So very quickly, Paul, if you don't mind. For some countries, is it possible to combine these kind of data that you're collecting with emissions data?
With?
Emissions data.
Admissions?
Emissions.
I heard this comment before, and we should do that. Yes, we should. I'm all for it. Yes.
Because okay. So.
That's a very good point. Yes, definitely. Thank you, Chris. Okay. Oh, sorry. I need to speed up. So, our goal was then to say, how do we get? We want to get subnational GDP. Basic idea. Think of a countless production function. We set it up like that. We divide by L, take the logs. We have basically the A is the technology, the total factor productivity. We have a constant, and we have this region-specific shock. And that's our stock standard empirical equation. So in the first step, simply what we do is we use the official GDP per capita data at the for 209 NUTS2 regions in our 25 countries. We regress the log of GDP per capita on capital, and we get this coefficient here. And of course, we only have 209 observations because we only have a cross section. And then basically we use the estimated coefficient alpha, the total factor, our proxy for total factor productivity, which is the epsilon from equation 4, from here. And then we replace the official K data from Eurostat with our predicted K from this exercise here, okay? We plugged it in and calculate basically, I label it calculated GDP. I don't know, maybe, I guess some of the macro people might not like that. And then all we do is we use this calculated GDP measure and we regress the official GDP data on this calculated GDP and get a correlation coefficient between what we have constructed using the satellite-based fixed capital and see how well it correlates with the official GDP data using various capital stocks and things like that. So we do relatively well. So we get a coefficient of 0.7. And then, because our benchmark is basically this light data, so the first goal is to say, can we perform better than the light data in the cross section? And actually, there's been recently quite some discussion, and most people agree that light data, especially the old generation light data, does actually relatively well when you correlate it with GDP. So the cross-sectional variation is pretty good. But if you compare it with our sample, and we use the light mean versus our measure, that's pretty good. Okay. Okay. That's that. Any questions on that? Yes.
Yes, do you know the intercept term in your regression of the real GDP, actual GDP on the predicted GDP?
Not from the top of my head. You mean from this regression?
Yeah, the intercept term.
Yeah, I don't know it.
I think it is an important parameter to me because it tells us the similar question to Yan raised, whether it is overestimated or underestimated for small GDP countries. Yeah.
Okay. Mm-hmm. No, I will include it the next time. Yeah. Now, so that's sort of the proof of concept stage. Before we want to go into Africa, or when we then switch to Africa, we realized that for Africa, we don't have this fantastic ground truth data because there are not that many OpenStreetMap people in Africa, plus the publicly available GIS data is not that great. Now, we then realized we cannot identify as many categories like the 17 as we use here. So we started off by just focusing on the bare minimum, which is roads and buildings. And we said, okay, with our approach, how well would we do if we predict capital just using roads and buildings? And so we do that here and we redo our analysis. And when we do that, instead of having 0.7, we get 0.6, which is still better than the light thing does. Okay. Now for Africa, there are a number of other issues. The main issue that we haven't solved yet is that for Europe, we were able to calculate the total factor productivity numbers by simply using the error term from the normal growth regression. Now in Africa, we don't have sufficient GDP numbers to calculate that data for each subnational region. Thereby, we just apply this naive approach that we have here. So that's sort of the side thing. The next problem is that for Africa, we don't have this great OSM coverage, which helped us to improve the ground truth issue. However, for some areas, we have pretty good OSM coverage. So for example, in Rwanda, there's a pretty good coverage. And in addition, what we have is there's drone imagery from an Open Cities AI challenge that segmented basically the challenge there was basically we have drone images and try to identify buildings, and we were able to use this data as well. And so long story short, we believe that even for Africa, despite not having complete OSM coverage with those two tools, we can do very well to train our algorithm to identify roads and houses in Africa, okay? And as I said before, to train the algorithm, we don't need complete coverage, because if we had complete OSM coverage, we would not need daytime imagery because we could just add up those numbers. And now, that's the statement, and here's sort of the proof. So here we have an image of a dirt track in Africa, which is just a very minor road. So it's not one of these major dirt roads in Africa that are actually considered major roads. It's an actual minor road. And here's basically the predicted lines that our algorithm would predict by seeing this image. And it actually did pretty well. I mean, the first time when we saw that image, we were pretty happy. Of course, there's some gaps here and there, but we are talking really about a minor road in Africa. And you can see there's a lot of, it's not a, for the computer, it's actually a very noisy picture. Okay, so sorry, I have to speed up a bit. Now in Africa, we calculate what we would then say local economic activity, and we are doing that at the so-called prior grid cell level. So there are a lot of papers now that use this unit of observation for subnational analysis across the globe. Prior is this Norwegian institute that provides us with a lot of nice data, and they divide up the world into these grid cells with the size of 55 times 55 kilometers at the equator. Now, what we did is we collect and that's why it's work in progress. So for 37 African countries, we have done the image processing, and we have mapped those to roughly 2,000 prior grid cells. And these are the grid cells here. Now, what we do is basically the unit of observations are these grid cells. We predict the capital using extracted road and building data from the 1 times 1 kilometer images and aggregate it up at this grid cell level. Then we combine it with population data from PRIO, and we use the estimated coefficients from the naive approach before. And we label the whole thing local economic activity, or LEA. We haven't found a better name for that yet. Okay, now, again, the benchmark is the light data, because that's the only proxy for economic activity that we have for those 2,000 grid cells. And the median light, so the light in that data is scaled between 0 and 63. The median light is close to 0. And that's normal. I mean, that's what Jen and Nordhaus told us. For in a lot of African countries and areas, it's just very black. Now our median value is 689. So this is not GDP, it's just the level, the measure that we get so far. Now, the interesting bit is, can we do a bit better compared to light? So when we look at West Africa, and on the left-hand side, sorry, when we plot the light data, the more intense red are the more developed ones, and we see basically that they pick up, some of the major port and capital areas in this area, and then, some development here and there. So that kind of confirms, an initial sniff test showing that, you know, more intense light is where more urban agglomerations are. But then you can see that there are a lot of the white one are blanks. So there's basically zero light. But when you zoom into these areas, you see, first of all, there's population there. And you see when you zoom into the daytime areas, there are buildings there and roads and things like that. Now in comparison, and so all these white things would be coded as zero economic activity in the nighttime light data that we all, or some of us have used. Now here, that's our calculated data. The first thing is, again, the more intense areas are, again, the more intense areas that are captured here. But then we have actually a bit more variation across space, and we hardly have any, or we don't have any missing observations or areas that are coded as zero. And the same goes actually for East Africa. So here we have Kenya and Somalia, where it's even more pronounced. The difference between the nighttime lights and our data. Now, one could argue, well, Paul, maybe you guys are just calculating sort of for all these, instead of having zero, you have just some positive value there, but it's, you know, subsistence level, and you don't have actually that much variation. So what I've plotted here now below are our LIA for the 681 cells where nighttime light is zero. And what we actually see is that actually in our data, there's quite some variation going on. So it's not just us finding a value of zero or replacing a value of zero by some positive value and calling it the subsistence level, but there's actually quite some variation going on, which is already, that makes this, so this alone ticks our first goal to say we want to improve on, you know, shedding some light where no light is, kind of thing. And the last bit to finish up is to say, okay, now how is this data useful? And that's, there we are just at the starting point, and we said in the first step we want to see how well does our data, how do results of study, do they change, or do we at least kind of confirm the results of existing studies when you using subnational cross-sectional light data when you use the LIA. So there's a recent QG paper by Henderson and others, and what they basically do is they examine the role of natural characteristics and divide them up. So natural characteristics that either affect agriculture or trade as determinants for subnational economic activity across the world. So it's, you know, towards this long tradition, or this long big literature in economics about geography versus institutions, and they look at geography. They argue basically these geographic variables are exogenous, and basically what they do is they use nighttime light in a cross section at the prior grid level as an outcome variable, and regress this outcome variable on a battery of natural characteristics, which they then subgroup and say, is it for long-term economic development, geographic characteristics that are beneficial for agriculture more important than geographic characteristics that are important for trade? That's in a nutshell. So we do that. Yes, I've said all that. And what they find is actually that agricultural variables explain much more variation in long-term economic development than trade-related variables. So that's their result, in particular for countries that developed early. Okay, so what we did is for a subset of grid cells for which we have our LIA, we take their data and match it, and then basically rerun their main specification. So they have this outcome variable, light per area, and then the ruggedness, temperature, precipitation, land suitability for agriculture, distance to the coast, distance to the next navigable river or a dummy. And then we regress the whole thing on, we replace light with Lea for the same number of pixels. And overall, when you look at it, is that most of the signs are the same. Of course, the size of the coefficient differs because they use data that's coded between 0 and 62, and our data is between 0 and 10,000. And for most, so in that sense, what we take these results at is that we find basically very similar results, except for ruggedness, where we find a different effect. Right now, we are not aiming at trying to explain the differences in these results. It's again just a first test to say overall, using our data in an empirical study and comparing it to these existing results, it does pretty well. Our R squared is a bit smaller than their R squared, and one of the reasons potentially that our data just has way more variation in there. So that's, yeah, that explains that. And in their paper, what they basically do, it's actually econometrically a very simple paper. They have this main specification, and then they run the specification with all the variables. Then they have a set of base variables, which creates an R square of 0.4. Then they just add the agricultural variables, see how much the R square improves, and then they include the trade variables instead and see the R square improves. And from that, basically, they conclude that if you add to the base specification just the agricultural variables, we see more of a bigger effect. And in our case, we find a similar effect. Okay, but of course, the scale is different. Yes, that was it. So basically, what we do in this project, we develop a new method or augment an existing one to detect physical infrastructure from daytime images. We use those to predict fixed capital at the subnational level to calculate a proxy for economic activity. And what we think is that this proxy for economic activity just helps us to get a more detailed idea of differences in subnational development, especially for Africa and maybe other less developed countries. And in addition, provides just a broader coverage in subnational economic development than nighttime light. Yeah, that's it. Thank you very much.
Thank you, Paul. If Leandro has a question, so Leandro, please.
Hi, Paul. For Africa, do you try to use mobile data?
Mobile phone data?
Yes.
Yeah. So there's the paper by Joshua Blumenstock who do that for one of few countries. We don't, because we don't have the data.
But in principle.
Yeah. So one thing, I think Blumenstock's paper is just for one country, and I think you need to rely on you need basically a mobile phone provider from the country to give you the data.
Yeah, but Paul, there's some new research which talks about how they are using phones to look things up on the internet, and the traffic from different regions of the world on Google or on these websites can be extracted using some APIs. And so that might actually, be what Leandro's point leads to, that, that data might be useful.
Okay. So 2 points. So Leandro, by all means, I think if we could get our hands on data that covers this mobile phone data Africa-wide, that would be fantastic. I mean, the best thing that I have myself is just the location of cell phone towers for Africa, but I don't know how many users there are. I mean, us ourselves, we collect this internet data worldwide on a daily basis for, taking 3 billion measurements a day. But for Africa, the issue is that the geolocation is not very precise. And Tushar, I think the search stuff is interesting, but I think when you go on Google, what is it, Google search or trends, Google Trends. So for America or Australia, you get sort of a subnational search trends by subnational unit, but it's still, most of it is at the state level.
Yeah.
There's none such a thing as at this pixel level.
Okay. Yeah.
But yeah. Yes.
Can I say, Paul, I know.
So Chris, Rod, Simon, and Ken in that order, please.
Sorry,
so Chris, you're first.
Yeah. Okay, sorry. 3 quick things. Paul, I know somebody who's probably got access to the complete data, universal data for Senegal, Cote d'Ivoire, and I think Ghana. So, I mean, if you remind me, I might be able to put you in contact. They were certainly offered the data from those companies a while back. And it might be only for a few years, but it's the universe of everything, including the number of characters in text messages sent, geocoded, etc. 2 things. One, I mean, I worry a little bit in terms of when you build your panel, there's going to be quite a lot of seasonality in some of the activities in Africa, whether it's with fishing or cocoa growing, or there's a whole bunch of things you might want to consider. And then I also thought there's quite a difference here between production activity and consumption activity. And it seems to me largely you're kind of capturing production activity, but also some kind of residential buildings. But certainly for, I don't want to say the vast majority, but for the majority of those in poor countries in Africa, I mean, there are things that you can observe from satellites, such as whether a roof, for example, is made from traditional materials or say a corrugated roof. And that might you be able to capture some aspect of consumption or wealth or assets through such observations.
Yes. So I had exactly that chat with Klaus, and his reaction was basically, yeah, we can do that, but it's not that easy for that large amount of I think I mean all the work from Give Direct and Johannes Haushofer and others, yes, that's, I think, no, I fully agree with this. Would be something that we would love to do. Yeah.
Rod, you want to go?
Yes. I presume the analysis is static, right? You're not taking measurements across time and observing a development process. You're comparing one location to another. At least that's my understanding of this. And I was perhaps I'm a little ignorant here, but a bit uncomfortable with taking buildings and your measures of fixed capital, especially in a poorer country, and then plugging that into a Cobb-Douglas function for GDP. I mean, given particularly that agricultural land is so important, and that development really is about shedding workers from agricultural land, right? So agricultural productivity rises in many poor countries much faster than productivity elsewhere, which is what enables the shedding of workers back into urban areas. Perhaps you capture that process with urban housing in the sense that the shedding of workers actually yields that. But I'm just not sure when you actually approximate your GDP numbers how you take account of the agriculture applications. A particular case in point, I was reminded when you showed us that satellite photograph taken in Europe, which had some clear spaces, some buildings, and quite a lot of forest. In Europe, forests like that are usually productive forests, right? They're usually forests that are regularly cut and regrown. And so that's productive activity also that I'm not sure whether you're counting or not.
So these are all very good points. The quick answer is we don't. For Europe, I mean, given the size of the agricultural sector as a portion of the GDP, it's less of an issue, but you're absolutely right that for Africa it is an issue. And I mean, one reason is that we are not, I think I mean, as you have seen right now, we are absolutely sloppy in terms of the economics terms we are using. So we are not, as I said, I mean, we said local economic activity, but probably it's not a good, even that is distracting. So we avoided using local GDP to claim that we, at least for Africa, can calculate GDP. So, and that's, I think, an issue that most of these alternative measures have. They call it, you know, a lot of them use economic activity, because the same thing applies to, I mean, that's one of the main critique points with nighttime light, that agricultural activity in Africa does not emit light.
Sure.
And at least we can do better to say yes, but at least we see that this productive capacity is then translated into some form of consumption or government investment through road building, and at least we covered that up. But yeah, I fully agree. These are the obvious downsides of the approach here.
But is it not possible to use the same technology to identify land use patterns as well, though? I mean, that is to distinguish agricultural from non-agricultural land, and therefore to actually put in your production function a land component.
Yes, there's that, and actually there's better satellite data out there on crop planting, so we don't even need to use our intensive thing. There's already satellite data out there using some other measures that can identify land use. That we should do that. That's a good point. Yeah, thank you.
Yeah,
Rob.
thank you.
All right, so we're running out of time, but like if Paul has the
I
time
have plenty of
to
time.
engage, right? Okay, perfect. So in that order, Simon, Ken, Sean, Michael. Simon, do you want to go first?
All right. Somehow I don't have that raise hand option as a host, so I have to raise my real hand. Paul, I just have this question. The way I see these two approaches, this light time, the light data and your data, is there any way that we can actually combine both? So the way I see these two, instead of a substitute to each other, is they are somehow complement to each other, because the light time data is probably better at the intensive margin, and then your approach is pretty good and compensate the extensive margin. So if we can somehow figure a way to combine both, like, you know, you have your approach has two grids that has same score, but in terms of the light, they are different, then combine the two can give you better information. Is that possible?
Yes, and I think we heard, yeah, it is, and I think we should also do that. But one thing that we try to overcome is that to provide at least some insights for all the areas where we don't have nighttime light.
Right.
So we could use your approach or do a combination to improve on our calculations for all those areas where we have nighttime light and combine it. I think that's something we should do irrespectively. But then for all the areas that have zero light, but we find economic activity, we don't have anything there. But I think all the comments that came from Rod and Chris and others on using, just adding up, I mean, there's so much other georeferenced and remote sense data out there that we should try that to see whether we can further improve. And these are combined to, you know, collecting road and buildings data. They are fairly easy to implement.
Okay.
Thank you.
And
my question or my comment was the same as Simon. You can view your data as viewing capacity, that is almost a fixed capacity. You multiply that by the rate at which it's used, which is picked up by the light data, then you get GDP. So you can think of the light data as entering multiplicative in the Cobb-Douglas, and you could probably derive some reasonable weights to give to each of those two complementary measures, because you need both. Before you can turn the lights on, you need some capacity, and that's measured by your capital-based measures, I'd say.
Yes. Yes, that's a good idea.
All right, so I'll
Thank you,
have to.
Kenneth.
Yeah, sorry. Yeah. I'll have to end the formal meeting at this point, but please feel free to stay back. And Paul said that he has all the time we need, so thank you, Paul, for that. Michael, if you're in a hurry, you can go before Sean, or otherwise, whichever way.
That's fine.
Okay, Sean, you want to go first?
Okay, thanks, Tushar. So I have two questions about these machine learning models. I think it is the core of your research. So one is, so why do you particularly choose CNN? So does it perform best among all alternatives available that you have tried? The second one is, now you are trying to compare the nighttime luminosity with your measurement. Okay, your measurement to me just an index, okay, based on this model. It's just an aggregation from features. So I'm just wondering, because there's so many features which can be extracted from the images of the satellite, and then which feature is most important? Because here, I think different features may perform better in some dimension in predicting GDP, but not necessarily in other. For example, the farmhouse and farmland may be better to predict the agriculture GDP. The residential could be predicted in consumption, and factories can be good in predicting manufacturing. So I think, yeah, so in that sense, okay, different composition of GDP actually can be predicted by different features. Their importance could be different. But now you combine all together to predict the same GDP. So that in that sense, it may be hard for the algorithm to decide which feature is the most important one to predict the aggregate GDP. But I think if you, for example, if you predict a different GDP with different models, could it be even perform better? This is my second question. I think following the comments by Ken and Simon, I think maybe you can also, because now you have a model, so you can put a lot of the features into your model, right? So one of the features is actually the nighttime light.
Yeah.
Then
So
in that way, you can incorporate the nighttime light in your model to predict better.
good point. Yes. So to the first question, the CNN. So the main reason why we use the convolutional neural network is because that's what Sean and Al did. And that was, at least at that time, the industry standard. And it's actually even the most recent ones. So the one paper by Marshall Burke that came out recently also uses a similar form like that. We have not tried other things, and in terms of which tool is better, I would need to defer that the more informed answer to Klaus, because he's the expert on that thing. Now, to the other question, you're absolutely right in terms of that we have many features and they could help us predict, as you said, different sectors. So what we did here was actually for Europe, and that's the only area where we have, I mean, at the NUTS 2 level, fixed capital by sector split up. So we fixed agricultural, industry, and service capital. And we did that thing to run the OSM thing. In fact, the 17 features that we identified are the main categories that are best to predict all these things here, irrespective of the sector. And we don't see much of a difference in our results. Yes, that's that. And I fully agree. No, I think I like the comment a lot. I have to think about more. So we could start off by just incorporating the light for our exercise in Europe and see whether we simply do better than we do right now. And then, but still, and then for Africa, I think, as I said, having something, I like the way that Ken mentioned, to think about it as capacity and then take another measure as something to use, you know, this capacity. So I think using emissions and land use is, and maybe mobile phone activity would be a good next step. Yes, these are all, yeah, very good comments. Thank you.
Yes, I think compared to the nighttime luminosity, because here now you have many features. Unlike them, they have only one dimension of the measurement. Because now you have many features. That makes you have some flexibility to predict different sector GDP separately, because okay, different feature actually play different roles in different sector of GDP.
Yeah.
But now you put them together, it's hard for the model to, so to select which feature is the best.
Yes. No, I fully agree. Yeah.
Yeah.
Michael?
Thanks, Tushar, and thanks, Paul. Great talk, fascinating topic. So a couple of things I wanted to mention, but I think they've been touched on in different, perhaps, words, but let me quickly go through. So one is, I fully agree, complement, if it's possible to complement the nighttime light data, I think that would be cool, rather than just looking at it as a substitute, which means, I think conceptually, which I don't know, but you've been thinking about this a lot more, but what elements would the nighttime light data be really good at that is perhaps better than your approach, and vice versa, and then sort of combining them in certain ways would be really cool. Yeah, so that's just confirming what Ken and Simon and others maybe. Another point is that Henderson paper includes country fixed effects, which means they only look at within country variation. And I wonder whether your approach would be better at identifying cross-country variation in some way. So I wonder how squares would look like if you take their without country fixed effects to your without country fixed effects. I haven't fully thought this through, but I just think the country fixed effects are sort of it's a big sledgehammer to resolve certain things. And I wonder whether you can, when you take that away, how your data would do. That's one thing. The other about the fixed effects, and that's my last point. I wonder whether you could sort of put in fixed effects for different populated regions. So cities, I think your algorithm, your machine learning might perform differently than in rural region, and there might be different stages. And I know you might not have detailed population data, that you can still see your bins, and I wonder whether that would sort of improve your predictive power in some regions and tell you in which type of regions it wouldn't work that well. Because I think population size in a certain sense also proxies what type of industry would be present there, whether it's agriculture, services, or industry mostly. So I think that's something that you could play with the fixed effects and different variations a bit more, maybe to see how well you explain results there.
Yeah, these 2 points are very good. I think, yeah, I like the just, you know, running the comparison with Henderson without country fixed effect is a really good idea, and then just looking at the heterogeneity. I think with the population data, you know, right now we have included it, but to some extent, I mean, all of us are cheating ourselves. So we use this data to some extent, because the population data that is used, so this gridded population data of the world, I mean, what it does is it takes census data. Sometimes you have information from the census, like geolocated information, but the gridded population of the Earth data uses nighttime light to allocate people in space, and then just look at the, when you aggregate that up, it adds up to the country total. So again, it relies on this nighttime light data, which again is an issue for Africa. So, but no, definitely we should do that. Yeah, thank you, Michael.
Cool project.
Thank you.
So Paul, if I can ask 2 quick questions. I think nobody, Sean, do you have any more questions? No, okay. All right, so Paul, 2 things. So first, basically following up on Rod's point that, you know, obviously the structure of the economy in different regions is different, but that also gives me an idea that you could actually, to some extent, document the extent of structural transformation that's happening in different parts of the world, just by using your method, and that could be a super cool paper, right? But two questions that I had, or one concern and one question was, so it's nice that you have all these options of using, say, emissions data and like the fixed effects, but this is at the end of the day, you're training the algorithm, and if there's a concern about overfitting, right? You might be able to like really perfectly fit the model on the data that you're training it on, but once you take it outside the data that you've trained it on, the model might not be that good, right? And we saw this in the Google trends and predicting influenza in the US, right? It happened. So I would say that there's some caution to be exercised when you use all that emissions data. I mean, emissions in Africa might be a very good indicator of where the industrial production is happening, but maybe not in France. There's some caution to be exercised there. The second concern, which is more to do with your the presentation that you showed us, was when you looked at how well your data did conditional on lights data recording a 0 value, right? Your mean was actually higher than the overall sample, right? Which, I mean, it could be that your data is super, super cool to catch that stuff, right? But to me, it's a matter of concern, right? I mean, it says that those white cells are actually having more activity, right? So how do you explain that?
Yes, actually, yes. Thank you for picking that up. So right now we don't have an explanation because I simply haven't had time to look into it just to see where this comes from. Yeah, and your comments regarding using additional variables is absolutely correct. Yeah, there are a lot of issues there, but I still think that, I mean, adding even the pollution data, I mean, we can use NOx data, but using, so the two widely used satellite data-based pollution products are NOx and PM, so particulate matter, and particulate matter is particularly bad for Africa because of all the sand. So we could also use NOx and yes, no, there's plenty to think about.
Yeah, my concern is simply that we have to be careful in terms of how the predictions based on these new parameters might change across space, right? Okay, Sean, a final point. Did you have one? Are you hand? Okay, no.
No, I don't have.
Cool.
Thanks. Yes, I think I have made it clear. So, my suggestion is it could be better to just predict the GDP in different sectors with different models, and then you can aggregate them up. I think that could be make your model. I'm not sure. That could be make your prediction even better.
Yes.
Yeah. Cool. So if there are no more questions, please join me in thanking Paul. Paul, thank you so much for taking out the time. Hopefully we'll see this paper in print soon and you in person here whenever the situation allows.
Yeah, thank you. I would like to say that was so far my most interesting webinar, because normally in webinars you get a few questions and then people go home, but I think my colleague Sasha Becker told me as well when he gave a webinar at UWA, he was super impressed that you have a lot of people showing up, a lot of interest. I think that's what it should be, because I mean all the webinars that are around, there's some fatigue. So seeing such a big crowd and getting so much input is, no, thank you. Thanks a lot. I really appreciate that.
Thank you. We hope we'll continue this, but thank you for the presentation. All right. Bye.
Bye,
everyone.
Thank you, Paul.